Hello everyone. In this video we're going to talk about continuity. Now continuity is the last section that we're going to discuss in chapters 2, and that also makes it the end of our first unit. So this is the last one before our first test. Now, continuity, we've talked a little bit about this in previous sections. Continuity is dependent, at least in calculus, if the limit as x approaches a of f of x equals f of a. Now that is the official definition, but there's three things embedded in there that you may not think about unless you actually are listed themselves. So let's think about it. The first is that the limit as x approaches a of f of x actually exists. That's the first one. The second thing is that f of a is defined. So it actually is real and is there. And the third is that the limit as x approaches a of f of x equals f of a. So there's three things embedded in this one definition, and all three must be applied if the function is continuous at a. Now, just because it is continuous at a does not mean it is continuous everywhere. So that is where our first examples come in. So it says identify where the function is discontinuous and state what condition they violate. So when they're talking about what condition they violate, they're talking about these three conditions that we just talked about. So that f of a is defined, that the limit as x approaches a exists, and that the limit equals the f of a. So what does discontinuous mean? Well, there's a couple of different ways you can think about it. Now, most cases they're talking about the domain, but you can also talk about the range. Most cases, though, it's the domain that they're really talking about, the x's in particular. So, we have any jump in the function will be a place where it is discontinuous. So let's see here. We have a jump here, a jump here, and then we also have some here. Okay? So let's take this one at a time. Alright? One at a time. So when x equals -2, now is f of a defined? Well, yes, it is. F of -2 is 1. It is defined. Does the limit exist? Well, no, it doesn't. Why not? Because you have a jump here, and the limit from the left is not the same limit as the limit from the right. Because of that, the limit at the number does not exist. So that is the condition that does not apply. Okay? Same thing where x equals 4, pardon me. The f of 4 does exist, and that is -7, but the limit as x approaches -4 does not exist because our limit from the left and our limit from the right do not agree. Therefore, the limit at x equals 4 does not exist. Okay, and this last one, when x equals 8, this one at f of 8, that's the problem. DNE, it's a hole, right? It's a hole, and there's no solid dot anywhere to take care of. So that is discontinuous there. Okay? Let's do another one. Identify where the function is discontinuous and state what condition they violate. Okay, so it is obvious, because we have a hole here, that it's continuous everywhere else, and it is discontinuous or may be discontinuous at that hole. So when x equals 1, we have a problem, or we may have a problem. Let's see. Well, f of 1 is 3. So that condition is accepted. So the limit as x approaches 1 is what? Well, the limit from the left is -3. The limit from the right is -3. So that condition works. So does the limit as x approaches 1 equal f of 1? No, it doesn't. So that is the condition that is violated. 3 does not equal -3, so these two do not equal, and thus it is discontinuous when x equals 1. Okay. So let's look at a piecewise function. What if they don't give us the graph? Okay, so the same 3 conditions apply because that is the definition of continuity, and our definition never changes. So just because they don't give us the graph this time doesn't really mean much. So determine if f is continuous at x equals 3. Why or why not? Well, that is conditional upon a lot of things, isn't it? And we can't really just look at it and tell this time, can we? Now, we could graph it ourselves, or we can do it algebraically. Now, since the last 2 examples were done by graphs, how about we do this one algebraically? So, grabbing our handy-dandy calculator, let's see what happens if we have this top part here at x equals 3. So 3 squared plus 4 times 3, which is 12, gives us 21 when x is 3. And 4 times 3 is 12. Okay, we can already tell that it is discontinuous at x equals 3 because those 2 numbers do not match. So the limit from the left does not equal the limit from the right, which is pretty much exactly what this says, doesn't it? So the limit from the left, which one would that be, the top or the bottom one? Well, the limit from the left means coming from this direction toward that direction, means we are in the negative numbers, so that would be the bottom. So the limit from the left would be the 12, and the limit from the right would be the 21. Now it is continuous from the left. It is continuous from the right as well. It's just discontinuous at 3 because they do not match. So be careful from there. So you can have a completely continuous function except at certain locations. So on what intervals is f continuous? They are talking about the domain here and the domain only. So you can write this in interval notation or set notation, but interval notation is more common. So the interval of continuity would be from -infinity all the way to 3, and then it is continuous on 3, right? It is continuous on 3, but then it skips. So then we restart on the other side of 3, and we have this together. So that would be a comma in between. So do be careful. You will need a comma, not a union, to have these. Now, why is this a bracket on the 3 of the left where it's not a bracket on the right? Well, think about the symbols themselves. We have greater than 3 on the right and less than or equal 3 on the left. Remember that if you have a less than equals or a greater than equals in interval notation, those will be brackets, and everything else will be parentheses, less than, greater than, or infinity, either way, for interval notation. Okay, let's have another one. Now, in these next 2 examples, we can actually cheat a bit because, as I've said in previous lectures, the rules of mathematics don't change. They never change. We're just adding on to the knowledge we already have. So if we can remember some of the stuff that we already know, and we can apply it to this new definitions, all of that works together and it still works. So let's see here. In this function here, h of x, We want to know if it's continuous. Well, that's a polynomial, isn't it? That's a polynomial. All polynomials are continuous. There's no holes in them. There's no place where they stop. They're not like the square root graph, that stops. And it's not like the rational graph that has asymptotes. Polynomials don't have a place where they stop, and they don't have holes. So all polynomials are continuous pretty much by definition of what they are. So we can say that the function is continuous everywhere, all real numbers. So we can write that with set notation or with interval notation, negative infinity to positive infinity. And it works just fine. As opposed to example 5 here, we have the function f of x, and we want to know where it is continuous. Now there's two things going on here, isn't there? It is a rational graph which do have asymptotes and thus have holes in their domain, and we also have a trigonomic function here. Well, trig functions, it depends, doesn't it? Because some have asymptotes and some don't. It depends on the function. But at least half of them do, and half of them don't. So all we got to do is remember which half. So the sine, cosine graphs are continuous. We know that. And that is a sine graph, so we're good. Tangent are not continuous. Neither are cosecants or cotangents. And we can always graph that into our calculator to double check. There's no problems with that. So sine is continuous, but the rational is not. So how do we do this for rational graphs? Well, if we remember our college algebra, we set our denominator not equal to 0 and solve. So x plus 3 does not equal 0. So x does not equal negative 3. And we can write that two different ways. So it is discontinuous at x equals negative 3, or it is continuous where x does not equal negative 3. Depends on how you want to look at it. But both are the same general idea. And we can also write this in interval notation. Remember, we would just skip over negative 3. So we would start at negative infinity, get all the way to negative 3, get insanely close to it, and then skip over it, and then restart on the other side of negative 3 all the way to the end. So both ways work, whichever way you would like to think about it. Now, along the lines of knowing our rules and laws of previous math classes, that comes directly in with continuity rules and continuous functions. So there are certain functions we can just take for granted that they are continuous. All polynomials are continuous, pretty much by the definition of what they are. Some trig functions, be careful on those. Some are, some aren't, so test them is what I would recommend if you don't remember off your hand. Sines are, cosines are, but the rest you may or may not remember, so it's always a good idea to double check. Now, inverses are as long as their function is continuous. So if f is continuous, then their inverse is continuous. That is true. Exponentials and logs are continuous, but only in that such where their domain is continuous as well. So be careful there. If they say all x, well, not so much. But if they isolate their x value, they are, and it does work. So it is conditional. So trigs and exponentials are conditional on where they are continuous, but as long as they are in those conditions, they are indeed continuous functions. Now, continuity rules, those are pretty self-explanatory, but as long as the functions you're working with are continuous at the location, then this works just fine. There's no problems. Even something as complicated as composition of functions, that is still continuous. And all of our rules still apply. All of those mathematical rules still apply. It's one of the reasons why I like math so much. Once you know the rules, you don't have to really think about it too much because they still work. So let's do something that seems to be really kind of annoying. Evaluate this lovely limit. Well, grr. Just looking at it, it doesn't really look that well, does it? You've got a rational function, which we know is not continuous, and you've got a cube. However, take a look. This is an x to the 5th function. And yes, it's in the denominator, but I don't see a way for that to have x equals 2 as a 0. You could even put it in your calculator, get the graph for it. Let's see. Pause the video, put that into your calculator, and see the function. So if you put this into your calculator, you'll get something like this. Now, notice I did not put the cube, because the cube doesn't really matter. It's the function that matters, not the cube. So this part, this is continuous, where x is not whatever number that is, not the asymptote. And since they're only asking me for x is 2, I'm good. So once we have confirmed that this is continuous where they're asking me for, I can just put this into our calculator just with the rules of limits that we learned before. So substitution. Put 2 in for all the x's, and you get 5 over 4 cubed. Well, 5/4 cubed is 125 over 64. No problems. So as long as we're not actually talking about where the function is discontinuous, we have no problems with what we've already done. We can do it just fine. That's the big difference. All those rules still apply. So as long as we're not talking about where the function is discontinuous, we can find the limits easily. Now on that note, that of course implies the next group. So find the interval where the function is continuous, which means we need to stay away from where it's discontinuous. This is a square root function. So we know that the domain must be greater than or equal to 0. So let's put that into our lovely doohickey. X minus 7 greater than or equal to 0, so x must be greater than or equal to 7. So as long as we are dealing with this particular interval, the function is continuous. Works great. And you can do that as either set notation or interval notation. Remember, the greater than or equal to means we use a bracket, and that's greater than, so we go to positive infinity, and it works fine. Now, what if we can't really do this the way they want us to? Well, we have to use something else. It's called the intermediate value theorem. So the intermediate value theorem basically says that given two locations on a function, they have to have somewhere in between them that exists and is on the function so that they must be continuous. As long as we have continuity, the intermediate value theorem is true. If we don't have continuity, we have a very large problem. Because if we don't have continuity, we'll have something like this, and then that, and then our line here. So if we start over here and end over there, there is no point that the middle will hit this invisible line that we're talking about. So continuity is essential for the intermediate value theorem to work. But as long as we have continuity, works every time. Woohoo! Okay, so let's take a look. we have used the intermediate value theorem to show that this lovely function has a solution on the interval -1 to 0, and then find the 0. Now this is actually one of the best ways to use the intermediate value theorem. We want to find the solution, the 0, of a function. So we can do some nice math of what we know, and we know that the 0 has to be between it, and we can get a reasonable guess from there. This was very essential back before we had calculators to do most of the math for us, especially the weird shaky math of trig. Okay, so this is a polynomial. We know it's continuous everywhere, so we're good. And we have a solution on the end. We want to prove that there's a solution between -1 and 0. So let's see here. The f of -1, put this into our lovely calculator. Or you can just take a peek and see. So -1 cubed plus -1 plus 1. So -1 cubed is -1. 2 times -1 is -2. So -1 plus 1 is 0. So this would be -2. And f of 0, that's easy enough. Well, that would just be 1. So the value on the left here is -2, which is, of course, negative. The value on the right is +1, which is positive. So the fact that we have negative on the left and positive on the right means that we have to go through the x-axis somewhere in the middle, which means that we have a 0 somewhere in the middle. So our intermediate value theorem has proven that we have a solution on this interval. Woohoo! We have continuity, we have negatives on the left, we got positives on the right, so we must have a 0 in the middle. That's what the intermediate value theorem says. So, we just need to figure out where it is. Well, how about you can use your calculator, you can use the graph itself, or you can do it algebraically. Any way works. This is calculus, so I'm not concerned with you proving your math knowledge of the basics. We're kind of glossing over those. So you have multiple options in which to find the 0 itself. You could use the graphically, you could use algebraically, you could use the factors. Any way is possible. Okay, so I'm partial to graphically myself, especially since I have my lovely calculator to make it easy for us. So if we put this into our calculator, we'll have something along the lines of that-ish. And we want to know what x is there. So when 0, that way. Okay, so what's x? It's got to be a negative. And once again, use your calculator. Make it easy on yourself. So, if you do this correctly, you should have x is approximately -0.59. Woohoo!